Hello everyone and welcome to the class. In our last class, we talked about the first law of thermodynamics and we saw that how the first law of thermodynamics, which is nothing but the conservation of energy law, is associated, can be applied during the thermodynamic process, and we saw that how when in a thermodynamic process some amount of energy, heat energy is provided, or some amount of heat energy is exchanged between the system and the surroundings, or work energy is also exchanged, how that two form of energy then transform into internal energy. Now this entire thing can also be explained on the basis of the total energy of the system. Now total energy of the system is the energy, summation of the energy, which is a summation of the energies of the internal energy and the work energy. Let's try to understand this in a very simplistic term. When a system comes into existence, the first amount of energy, minimum amount of energy that is required by the system for its own existence is the internal energy. After this system comes into existence, it starts to interact with the universe, interact with its surroundings. Depending on the interaction, the volume of the system may increase or may decrease or may contract. The volume of the system may contract also. That will result in change in the pressure, may be increased in the pressure may increase, the pressure may decrease. So when a system comes into existence, it requires a minimum amount of energy that is necessary for its existence only. After its existence, it starts to interact with its surroundings, and the interact happen in a pressure volume change way. Due to this interaction, the work that it does, the work that the system is do, or maybe the work that is done during this interaction, this work is due to the pressure volume changes. The work is, that's why known as the pressure volume work. And the energy that is associated, that is required to do this pressure volume work, is known as the pressure volume energy. That amount of energy and the internal energy for the existence of the system in total known as the total energy of the system. So what I'm trying to say, a system very first comes into existence, and a minimum amount of energy is required for that, for its existence. After coming to existence, minimum amount of energy is required to do the pressure volume work, to do the pressure volume work by the system or on the system, so the system can interact with its environment. So this both amount of energy is necessary for the functioning, total functioning of a thermodynamic system, for its existence and to do its work. So the total energy becomes the summation of this two energy. A new energy term, that's why is designated to this total energy of the system, known as the enthalpy. So enthalpy is nothing but the total energy of the system, which includes internal energy and pressure volume work energy, which is designated as capital H and is given by H equals to U plus PV. U is the internal energy of the system that is just came into existence. PV is the pressure volume or work energy that the system has to interact with its surrounding by doing some pressure volume work. The total amount of this, total summation of these two energy results in the total energy of this system, that is the enthalpy of this system. Now the change in the enthalpy, what this means. The change in the enthalpy means that supposedly this is a system that we are observing. It has confined a certain amount of gaseous molecules. Let's say it's an ideal in nature. In this particular state, this one have an internal enthalpy of H1. After doing some process, supposedly the state of this thermodynamic system changes to this one, and at this state the enthalpy of the system is H2. So the during this process, enthalpy, the total energy of the system, has changed, and the change is given by delta H equals to H2 minus H1, change in the enthalpy. Change in the enthalpy. Let's take another example. Supposedly A of A reacting with B of B and producing C of C and D of D. The enthalpy of A reactant is HA. The enthalpy of reactant B is HB. So the total enthalpy of the reactant is HA plus HB. Similarly, the enthalpy of product C is Hc. The enthalpy of product D that has been produced is Hd. Therefore, the total enthalpy of the product is Hc plus Hd. So during this change that has occurred through this chemical reaction, reactant has been transformed to product. During this chemical transformation, which is also a thermodynamic transformation, the total energy changes of the system changes, and that will be given by delta H equals to delta H total energy of reactant minus of total energy of the product minus of total energy of the reactant. Now this has been given because the total energy, the change in the enthalpy, is given by in all in all thermodynamic process as delta H equals to H of final, total energy of the final state, minus of total energy at the initial state. Let's take an closed thermodynamic system. This is a closed thermodynamic system. An ideal gas has been enclosed within this. It has a volume V1 and internal energy U1. In this system, QP amount of heat energy is given at constant pressure. After this Q amount of heat energy provided at constant pressure to this system, a new resultant system will be established for this thermodynamic system. At this final state, the volume becomes V2 and the internal energy becomes U2. Now, at the initial state, the enthalpy of the system was H1, and it can be given as U1 plus P into V1. P is the pressure of the system. At constant pressure, the process has occurred, so the pressure will at the final system is also going to be P. And the enthalpy at final state is going to be H2, which is equals to U2 plus P into V2. This is the equation for the enthalpy at the final state, and this is the equation for enthalpy H1 at the initial state. So the enthalpy has changed due to this process. So the change in the enthalpy can be given as delta H equals to H2 minus H1 or U2 plus PV2 minus of U1 plus PV1, or this can be
written as delta H equals to U2 minus U1 plus P whole into V2 minus V1, or delta H equals to delta U change in the enthalpy plus P whole into delta V. Now we can say that we can ask that why at constant pressure condition we had applied in this example that we are talking about. Most of the chemical reaction happens against a constant external pressure, that is against the atmospheric pressure, against the constant atmospheric pressure. As most of the chemical reaction happens against a constant pressure, atmospheric pressure, the most of the chemical thermodynamic process happens in a constant pressure condition. That's why we are considering this particular concept, because most chemical reaction happens at constant pressure and we are talking about chemical thermodynamics in predominantly. That's why we are considering these conditions specifically. Now at constant pressure, the change in the enthalpy equation mathematically becomes delta H equals to delta U plus P delta V. Now from first law of thermodynamics, we know that delta U is nothing but QP minus of P delta V. We know that from first law of thermodynamics, plus delta V is there. These two value will cancel each other, resulting in delta H equals to QP. So from the first law of thermodynamics, a modified definition for change in the enthalpy can be written. Change in the enthalpy can be drawn as change in the enthalpy value is the value equal to or equivalent to the amount of heat energy that is accepted by the system at constant pressure condition. If a thermodynamic process occurs in a thermodynamic system at constant pressure, the heat energy that will be absorbed by the system or the released by the system, that will be equal to the change in the enthalpy in the system. That is the thermodynamic definition of change in the enthalpy. Now why this definition is necessary? Because the basic the basic definition of enthalpy says that enthalpy is the total energy of a system, which is the summation of the internal energy of the system and the pressure, volume, work energy of the system. Now internal energy of the system cannot be calculated, cannot be calculated directly, cannot be observed directly. That's why enthalpy of the system, total energy of the system, for a thermodynamic state also cannot be determined directly, but the change in the enthalpy, the change in the total energy of the system, the change in the enthalpy of the system can be calculated with experimental value, can be calculated. That is why by the definition of the change in the enthalpy is nothing but the difference between the enthalpies between two states. The delta H by definition is the subtraction between the enthalpy in the final state minus of the initial state. But by basic definition, it means that the if a system, thermodynamic system, undergoes a thermodynamic process at constant pressure condition, then the heat energy that will be associated with its with the change will be equal to the change in the enthalpy of the system. That is the basic definition of the system. Now we have established this definition, change in enthalpy definition, from the thermodynamic system as QP, heat energy associated with the thermodynamic process at constant pressure. Let's try to establish the change in the internal energy definition from this way also. Now, we know that delta U equals to Q minus of delta P dV. This is the mathematical form of the first law of thermodynamics. Now, if this process occurs at constant volume, in that case delta V becomes 0. This will give minus P dV 0. Then this equation becomes delta U equals to Q V. That is, the change in the internal energy by definition is the heat associated with a thermodynamic process for a thermodynamic state when the process is happening at a constant volume. So by definition delta U is nothing but U2 minus U1. This is the definition of change in the internal energy. The difference between the internal energy, or the difference of internal energy between the final state and the initial state of our thermodynamic system. But we cannot actually calculate the internal energy directly like this. So what is going to be the thermodynamic definition of change in the internal energy? The thermodynamic definition of change in the internal energy is nothing but the heat energy associated with the thermodynamic process for the thermodynamic state, thermodynamic system, in which the process is occurring at a constant volume. Then what is the definition of the change in the enthalpy? Change in the enthalpy is the heat energy associated with the thermodynamic process of a thermodynamic system when the process is occurring at constant pressure. Heat associated at heat exchanged at constant pressure is the change in the enthalpy. Heat exchange at constant volume is the change in the internal energy. Enthalpy is a state function. It do not depend the pathway through which a thermodynamic process has occurred to reach the resultant state. Like let's say this is the a thermodynamic system of a ideal gas confined in this enclosed in this container. This system has an enthalpy of H1. After doing some thermodynamic process, the system has reached its resultant state, which is having a enthalpy of H2. So the change in the enthalpy delta H is going to be H2 minus H1. This is so far we know that. These H1 and H2 and H1 are nothing but the enthalpies at the final state and the initial state. The pathway through which this process has occurred to reach the final state from the initial state has nothing, have no influence over the magnitude or the values of the enthalpies. So the enthalpy is a state function. So the change in the enthalpy also, because in the change in the enthalpy is nothing but the subtraction between the enthalpies of final state and initial state. Let's say instead of this direct transformation, the initial state has changed at first to a intermediate state of this state of, and in the second process, in the second thermodynamic process, this intermediate state then changes to the final state. So we have done two different pathways. In the first pathway, a direct thermodynamic process has resulted in the final state, and in the second thermodynamic process we are doing two state in which we are at first reaching to an intermediate state, then that intermediate state reaches to the final state. Then in the both case, if we try to calculate the change in the enthalpy, we are going to calculate by subtracting the enthalpy value at the final state of the minus state. We are from the final state, we are going to calculate the change in the enthalpy value by subtracting the enthalpies of the final state and initial state. That is, delta H equals to H2 minus H1. We are going to do that only. The pathway that we are going to follow is having no influence over the change in the enthalpy values. That's why delta H is also a state function. H is a extensive property, so is delta H. Delta H is also an extensive property. Now by definition, extensive properties are those properties which depends on the constituent particles, the number of constituent particles. Now H is by definition is the total energy of the system. Total energy of the system. Now let's say this thermodynamic process that we were talking about. Each particle have an H value. Each particle have an H value. Let's say that this is the particle, this is also have an H value. This is the particle, this is also an H value. So this H value that each particle have, let's say that there are 5,000 in particle that is creating this thermodynamic system. Each one having an H value. So the total energy of this system, capital H, is going to be 5,000 multiplied H. H is the value per molecule, per particles. Let's say that we are taking this similar thermodynamic system, but now for 5 lakh molecule, 5 lakh particle. So we are going to multiply 5 lakh with the enthalpies of each particle. This will result in this amount of total energy, which is different. So the total energy of the system is depend on the total number of particle present within the system. That's why enthalpy is an extensive property, because enthalpy is nothing but the total energy of the system. Total energy of the system depends on the total numbers of particle present in the system. So enthalpy is depend on the total number of particle of the system, so as delta H. But each enthalpy of each particle, enthalpy of each particle, per particle, enthalpy of per particle do not depend on the numbers of particle, because each particle have its own numbers of enthalpy, own amount of enthalpy. So what I'm trying to say, H and delta H of the system is an extensive property. Depends on the numbers of constituent particle present within the system. But H or delta H per particle or per mole is an intensive property. Do not depend numbers of particle present in this system, but nature of the particle. These two things we need to remember. I'm going to say it again. Enthalpy of the system or change in the enthalpy of the system depends on the numbers of constant particle present in the system. That's why it is an extensive property. But the change in the enthalpy or the enthalpy of per mole or per particle of the system do not depend on the numbers of molecule or numbers of particle present within the system. It depends on the nature of the particle, not the numbers of the particle. That's why it is an extensive property.